Mm-hmm.
I hope you're doing well. In this video, we'll be calculating the planar density for BCC planes, and we can see we have a variety of planes in here. After this video, you'll find answers to all of your possible queries about planar density calculations, like how to find out the area of the plane, how to calculate the contribution of atoms to the plane, and how to know that which atoms are actually contributing to the planes and which atoms are not. So there is a systematic way which gives you 100% answer without any ambiguity, so that you'll be, crystal clear about what you are doing, and there will be no confusion. Especially related to 111 plane, there is always a confusion like whether the body centered atom contributes to the plane or not. So this video contains a complete method, so stay tuned, keep watching till end. It's a complete package that will help you to ace the planar density calculation for whichever cubic structure it is, whether it's BCC, FCC, or simple cubic. It applies to all kinds of planes and all kinds of crystal structures. Let's find out the planar density for 100 plane in BCC structure, and for that purpose the first step is to draw the plane. Draw the plane inside the cubic structure or cubic unit cell. Alright, so the first index gives us the x-intercept, the second index gives us the y-intercept, and the third index gives us the z-intercept. And how we can calculate the intercepts from these indices? It's really simple. We just need to take the reciprocal of each of these indices and we'll get the intercept corresponding to the index we are considering. So let's do that. Let's calculate the intercepts, and I usually do it in table form because whenever you are solving this problem in exam, it looks presentable. So here we'll write down the indices. First is H, K, and the third is K, L. So 1, 0, 0. Next step is to take reciprocal. Taking reciprocal. So reciprocal means dividing by 1. Okay. 1 divided by 0, 1 divided by 0 here. So 1 by 1 is 1. 1 by 0 is infinity. And 1 by 0 is infinity here as well. So the final intercepts that we have got for the plane is 1, infinity, and infinity. So these are the intercepts. This is the x-intercept. This is the y-intercept. And this is the z-intercept. Alright, as we have found the intercepts, now we need to draw the cube inside of which we will be drawing this plane. And this is a cube. Since all of the indices are positive, so we'll be taking this point as all positive origin, and this is x-axis, this is y-axis, and this is z-axis. Alright, and we can see here that we have x-intercept, which is 1. So starting from origin, we'll move 1 unit along x direction to the other corner of the unit cell, which means we have moved 1 unit. 1 unit means starting from origin or from one corner to the other corner along x direction is actually 1 unit. So this is one of the point on the plane. And we can see here that the y-intercept is infinity. Y-intercept is infinity. It means that we have to draw parallel lines from the point that we have found on the plane. This is x-intercept and this is the point on the plane. Okay, this is one of the point that we have found for the plane under study and under consideration. So this is one of the point, and from that point we'll draw a parallel line along y-axis because its intercept is infinity. This is how we deal with infinity every time. Whatever points you have got for the plane so far, draw a parallel line from that point along the direction which has infinity as intercept. So since y-intercept is infinity, this is y direction and this is y direction. So from this point we'll draw parallel line along y direction and we'll stop to the other corner of unit cell here. Okay, we stopped here. So this is another point. This line is also included as part of the plane. So this is another point on the plane and this is also a point. Now the z-intercept is infinity. We can see here. So we will be drawing parallel lines along z direction from each of these points. So this is like from this point onwards we'll draw vertically upward, which is direction parallel to z-axis. So we'll stop to the other corner of the unit cell. Similarly we'll do it here from here also. and we'll stop to the other corner of the unit cell, and here we go. Now we'll join these 2 points together parallel to y direction as well. So this is the plane whose planar density we wanna calculate here. Okay, this is like the front wall of this cube. Okay, so now we have drawn the plane, and this is our plane 1 0 0, and now we need to calculate the planar density, and for that purpose let me write down here the formula for planar density, that is equals to capital N divided by A. Now what is capital N and what is capital A? Let me write it. I'm using sigma sign to represent planar density, that is equals to net number of atoms centered on the plane divided by the area of the plane. Alright, so here the definition of capital N is really important. Here the word centered is central. Alright, this is really important word in here. All those atoms which are actually centered on the plane will be considered to be contributing to the plane. And if atom center is not lying on the plane, if atom center is not intersected by the plane, then that atom will not be contributing to the plane. Okay, so it will not be considered as contributing to the plane. But all those atoms whose centers lies on the plane, all right, whose at least centers lies on the plane, will be contributing to the plane, and their contribution will be calculated. All right, so let's see how this works. And we have this figure, and we'll be calculating its area, and let's see that how we can do that. First of all, I'm gonna calculate the area of the plane, and then we can have a discussion about the number of atoms that are centered on the plane and so on. So we can see here that the area of the plane is really simple. We can see that it's a square shape since it's a cubic structure, and let's say let the lattice parameter be A. Okay, you have to write down this formula first, and then you'll write down this thing. You can call it as equation number 1. After that, you are supposed to write that let A be the lattice parameter. A be the lattice parameter of the cube. And we know that in cube all these sides lengths along axis directions are A. So we can see that this length is A, this length is also A, and this length is A, this length is A, and this length is A as well. So we can see it's a square, and area of square is simply area of square plane is equals to A dot A, product of two sides, any two sides. So it's A dot A equals A square. It was really easy to calculate since we can see that the figure was really simple. And now let's calculate the net number of atoms lying or centered on the plane. Centered on the plane is the better word to use in here. So we can see here that it's a body-centered cubic structure, but this plane is lying on the wall, so there is no way that the body center atom is involved in here. That's obvious. And we can see here that there is a corner atom in here, there is another corner atom in here, this corner atom and this corner atom, because we can see that we have atoms at each of the corner of the unit cell. So these atoms would be lying in here, and there is no other atom that could be intersected by this plane, because rest of all the atoms lie on the other corners of the unit cell, which are on the back side of the this room. This is like a room, and these corners are not a part of this plane which is on the front wall. So only these atoms will be contributing to the plane, and the body center atom obviously will not be contributing to the plane. And one of the reason is that we can see the definition of net number of atoms centered on the plane, which means that an atom would be contributing to the plane if its center lies on the plane. Okay, if its center is also a point on the plane. So we can see here that the center of these corner atom is here. Okay, we know that the corner atom's center is also at the corner of the unit cell. This corner is also a center of this atom, and similarly this corner is also a center of this one atom. And we can see here that the center is here, but the plane is here. So we can see that their centers are outside of this plane, so they will not be contributing to the plane. And similarly, the body center atom is somewhere at center of the unit cell, while the plane is here on the wall, and it's not passing through the center of the unit cell. So the center of body center atom is not contributing to the plane. So that is how you may know about it. And this is a really simple case. As we can see, there is no complexity involved in here. But when we'll be considering the other planes, including 200 and 112 and also 111, we'll see this case coming over here, that we'll have some confusion in here, and we have to use this concept to evaluate that which atoms are contributing to the plane. So the fact that if the plane passes through the center of the atom, then that atom will be contributing to the plane. If the center of the atom is not intersected by the plane, then it means that atom is not contributing to the plane, and there is a mathematical way to do that, and we will see that way in the end of this video if you're curious. So let's see how to find out the contribution of these atoms to the plane. There is a well-defined method that I have established myself to calculate the net contribution of atom. So what you have to do in order to calculate the contribution is, we can see here that these are the circles, and the total angle of circle is 360. Okay, so what you have to do is to find out the angle or the part of the atom which is inside the plane. We can see here that only this is the plane, okay, and only this part of the atom is inside this plane, and rest of all the part, we can see rest of all the part is outside of the plane. So the whole of atom is not contributing to the plane, only a part of it. So how to calculate that part? We can do this by finding out this theta. Okay, we'll see how to calculate it by finding out this theta and dividing it by the total angle of the circle. So the result that you will get is the contribution this atom is making to the plane, and this definition and this method works every time. Okay, whether it's any kind of plane, all right, so or any kind of unit cell you are considering, it's true everywhere. So you will be dividing theta by 360 and you'll get the contribution. For that purpose, we should know what is the angle between these two lines of the plane, angle between these two lines of the plane, angle between these two lines of the plane, angle between these two lines of the plane. These are actually the thetas for each of these atoms. And since it's a cubic structure and it's the wall of the cube, we know that in cubic structure this angle is 90 degree. This angle is 90 also, and this is 90, and this is 90 as well. So what you have to do is to divide 90 by 360, and you get 1 by 4. So this atom's contribution to the plane is 1 by 4. This atom's contribution to the plane is 1 by 4. 1 by 4 by this atom as well, and 1 by 4 by this atom as well. So at the end, what you have to do is to add them all. 1 by 4 plus 1 by 4 plus 1 by 4 plus 1 by 4, or simply you can we have 4 atoms and all of them have 1 by 4 contribution, so you can do it that way as well. 4 cancel, so it's total so it's total 1. Okay, net number of atoms is 1. So 1 is net number of atom, and a square is the area of the plane. Now we need to put the values in equation number 1 here to calculate the planar density. So planar density for 100 plane in BCC equals 1 over a square. Okay, this is the planar density for 100 plane in BCC in terms of lattice parameter. And if we wish to express this planar density in terms of atomic radius of the atom making up the structure, then what you have to do is, as we know that there is a relationship between the atomic radius and the lattice parameter, which we can easily calculate. A equals 4r by under root 3. This is the relationship between the lattice parameter and the atomic radius of the atom making up the BCC structure, and this is only true for BCC structures. Okay, for simple cubic and for FCC there is a different relation because the assembly of atoms is different, the arrangement of atom is different, and that makes the difference between all of them. So it's true for BCC structures. Now we can put into this expression in order to get the planar density in terms of atomic radius. So it's A, and A squared will be equals to 16, taking square on both sides. So it's 4 square, which is 16, r square divided by 3. So we can put it right in here, 1 divided by 16 r square divided by 3. So 3 will go upward, and it's 3 by 16 r square. This is the planar density in terms of atomic radius. This is the planar density. Density in terms of atomic radius r of atom making up the lattice. Alright, so in this way we have calculated the planar density for 100 plane, and I'm not gonna mention the method to know that which atoms are contributing or not for this particular plane because it's not needed, as we don't have any confusion in here. But for those planes in which there will be confusion, I'll be using that method. So yes, it has units of atoms per meter square. Okay, since it's area in the denominator, so it's per meter square. So for example, you got 3 multiplied 10 to the power 22 results. So how you are gonna write the units? Here you'll write atoms, then space per meter square. You can also write it like that, atoms slash meter square. Slash means meter square is in the denominator. Okay, so that is it. Let's calculate the planar density for 110 plane in BCC, and for that purpose, first of all, we need to draw the plane inside the cubic unit cell. Alright, so for that purpose, we can see the first index gives us the x-intercept, the second index gives us the y-intercept, and the third index gives us the z-index. Oh my god, what I'm saying. The third index gives us the z-intercept. Okay, so how indices gives us the intercepts of the plane? So this is really simple. We just need to find out the reciprocal of each of these indices and we'll get the intercepts. And intercepts are the ones that helps us to draw the plane inside the cubic unit cell. So let's calculate these intercepts first, and I always do it in tabular form because it looks presentable when you are doing it in exam. So that is why I do it, so that you may be able to follow it easily. And this is H, K, L, and here we are writing the indices of the plane which we are wishing to draw. First index is 1, second is 1, third is 0. We'll take operation, which is we'll apply an operation which is taking reciprocal, and this is a single operation that we need to apply on indices in order to get the intercepts. So it's 1 divided by 1 divided by 1 divided by, taking reciprocal mean dividing by 1. So 1 divided by 1, 1 divided by 1, 1 divided by 0, that is equals to 1, that is equals to 1, that is equals to infinity. So here we have 1, 1 and infinity. These are actually the intercepts. Alright, so the first is x-intercept, second is y-intercept, and the third is the z-intercept. If you know, then you know that intercepts are actually the point where the plane touches the axis line. X-intercept is actually a point where the plane touches or cuts the x-axis. Y-intercept is actually a point where the plane cuts the y-axis, and z-intercept is the point where the plane touches the z-axis. Let's draw the plane. And okay, this is the x-axis, this is y-axis, and this is the z-axis. Since all of the indices were positive, that is why we are taking this point as origin, and this will be the x-axis, this is the y-axis, and this is the z-axis. Now let's draw the intercepts. And for intercepts, you always have to start from origin. Okay, first we'll mark the x-intercept, which is a single point. Okay, so let's mark that point, which is 1. X-intercept is 1, which means starting from origin, you'll move 1 unit along x direction to the other corner of the unit cell. So starting from your origin, you will move along x direction to the other corner of the unit cell. Yeah, this is actually point 1. All right, so point 1 means starting from one corner of the unit cell and stopping at the other corner of the unit cell along any axis direction. So since it was x-intercept, so that is why we moved along x direction from one corner to the other corner, which is 1. Here in cubic structures, what we mean by 1 is like we start from one corner of the unit cell and we stop at the other corner of the unit cell, okay, along x direction. So since it was x-intercept, so we moved along x direction, and this is the point, this is the x-intercept, and it is one of the point on the plane. Now let's draw the next point, which is y-intercept, and for that purpose we'll start from origin again, and this is the y direction. Starting from origin, we'll move to the other corner of the unit cell, which makes the whole length 1. So this is 1. This is the point 1 along y direction, and this is the y-intercept, or we can see the point where the plane cuts the y-axis. So this is 1. This is another point on the plane. Next, we can see the z-intercept is infinity, and by infinity, how we treat infinity while drawing the plane. So it is like the points that you have already found, okay, you always found, and mark the points which are not infinity. Okay, we deal with the infinity at the end. Luckily this was the end point as well. So here we will do that. From each of these points we'll draw parallel lines along z direction. Okay, so we can see here that this is one of the point on the plane. So I'll draw parallel line along z direction, which is vertically upward, and where I need to stop is the other corner of the unit cell, or the corner of the unit cell. So I'll stop here. Okay, so this is the part of the plane. Now from this point I'll also draw parallel line along z direction, which is this, and I'll stop to the other corner of the unit cell, which is this point. Next, we need to meet, okay, these points together to form a figure, closed figure. So that is how we have drawn the 1 1 0 plane. All right, so this is the plane, and let me shade it. This is its diagonal plane. Okay, we can see the plane now, and let's calculate the area of this plane, and then we'll calculate the net number of atoms centered on the plane. And for that purpose, area of plane. Now this shape is rectangle, okay, and I want to mention one of the fact that will help you in your whole life, okay, in physics and solving other mathematical problems that involves geometry or figures. So always keep that in mind, that a line which is parallel to z direction, okay, which is wholly vertical, and the other line which is lying on xy plane, okay, which is lying anywhere on the xy plane, but it should be on xy plane. So if there is a line that is parallel to z direction, and there is another line which is lying anywhere, like anywhere on this xy plane only, the angle between this vertical line and that random line on the xy plane is always 90 degree. It's always 90 degree, and it is because x, y and z directions are perpendicular to each other, and a line that is lying on the xy plane is always perpendicular to the z direction, always. Okay, I have that mathematical method to prove that the angle between this z direction and this line is 90 degree. but I want to give you a general rule that holds everywhere. For example, if this line would have been like that, like that, like that, or like that, wherever it is, but on xy plane, the angle between z and that line would have been 90 degree. Okay, so this angle is 90 degree. And why I am bothering to mention that this angle between these consecutive lines, this line and this vertical line and this line on the xy plane has 90 degree angle. By saying so that the angle between these inner consecutive lines is 90 degree, I'm just proving that this figure is a rectangle. Alright, and in a rectangle what happens is that the opposite sides are of equal length. Alright, we have the upside and the downside which are of equal length. The side lengths are equal to each other and the inner angles are 90 degrees, so it makes a rectangle. While there is another figure that we call as parallelogram, in which the angles are not 90 degrees, so the formula for the area is different. So you have to identify which kind of shape your plane has and use the formula for finding out the area accordingly. So that's a kind of discussion that is important because it will help you to identify the formula that you are supposed to use to find out the area of the plane, because area of plane is sensitive to what kind of shape this plane has. A rectangular shaped figure, its area is actually equals to length into width. Okay, two unequal size, product of two unequal size. But if it would have been a parallelogram, you know that in parallelogram two opposite sides are equal to each other, but the angle is not 90 degree, and the formula to calculate the area of parallelogram is different. Alright, so this angle does matter when you are calculating the area of the plane. So that is why I was mentioning in here that whenever you have these vertical lengths which are parallel to z direction and a line which is lying on the xy plane and whose z component is not changing, okay, we can see that this line has always z equals to 0 as its point, and this line is also having z equals to 1 as constant point. So they are not changing along z, but they are changing along x and y, so they are lying on xy plane, and this length is, if it's at constant z point, is always perpendicular to the z axis. Okay, that is what I'm saying. I hope you got it. That was too much explanation, but for those who are seeking the depth of everything, who wants to learn something new that can help them later in future as well, this video is actually a really descriptive video. I have also uploaded a video which was less descriptive and that contained less details, so you can watch it if you don't want these extra details, but these details always help you. They are not unnecessary, and yeah, that is something not all of the people or teachers teach their students, and I think they are really important skills to understand the relationship between different axis lines and what are happening in here. So we can see here that it's a rectangular shape and the consecutive angles are 90 degree. All right, so we have proved it. And here the area of the plane is actually product of this quantity, this length and this length. This is the length and this is the width, so product of these two quantities. We know that this length is a, but we need to determine this length. This is the diagonal length and we need to calculate it. There are two ways to calculate it. One is to use the Pythagoras theorem that mostly teachers use, and the other is to use the distance formula. And I always prefer distance formula because distance formula is always there. There are the cases where Pythagoras theorem doesn't apply or the Pythagoras theorem makes it really complex. So I'm going to use the distance formula. For that purpose, what we need to find out is coordinates of this point and coordinates of this point, which is super easy. So coordinates mean starting from origin, how much you have to move along x, y and z direction to reach to that point. Okay, so it's like a map or direction that you're giving to some random people to reach to that point. So what you have to do starting from origin, you have to move 1 unit along x direction and you have reached the point. You don't need to move y in z direction. So it means 1 along y, 1 along x, 0 along y, and 0 along z. These are the coordinates of this point. And similarly, for here, starting from origin, you have to move 1 unit along y direction to the other corner of the unit cell, and no motion along x and z direction was needed. So these are the coordinates of this point: 0 along x, 1 along y, and 0 along z. These are the coordinates of this point. Now let's find out the length. Let's call it as d. Okay, we want to calculate d now, and I'm going to use the distance formula, which is d equals under root x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square into a. We need to multiply the lattice parameter in here because they're all in fractional numbers, like 1 means the total length into a means this length is a. Okay, so we need to multiply by a whenever we are finding out the area of the plane or the length of the plane. Okay, because we need to have a lattice parameter involved in here. And yeah, this is here x2, y2, and z2 are this point or this point. You have to just name it like this. Let's say x1, y1, and z1, and this is x2, y2, and z2. You can also take it as x2, y2, and z2, z1, z1, x1. That doesn't matter, order doesn't matter, so you have to choose one of them. Okay, it's up to you which one you wanna choose. So x2 minus x1, 0 minus 1 whole square plus 1 minus 0 whole square plus 0 minus 0 whole square into a. Under root minus 1 square is 1, 1 square is 1, 0 square is 0, and it's 1 plus 1 plus 0 is 2, under root 2 into a. That is the length. And you have seen that it's so easy. It was really easy, no? So whenever you are wanted to find out the length, just find out the end points of the length and end points of the line and use distance formula to calculate the length. Okay, it's d equals under root a. This is a and this is under root 2a. So the area of the plane is actually under root 2a square. Alright, so this is the area of the plane. We have successfully calculated the area of the plane. Now we need to calculate the net number of atoms lying on the plane. And for that purpose, we need to see that which atoms and their centers are lying on the plane. So we can obviously see that these corner atoms would be the corner atoms have their center at the corner as well. So obviously the corner are the part of this plane, so they are obviously hence contributing to the plane. Okay, what about the central atom? Is there any chance that maybe this plane is not passing through the center of this cube? And since the center atom which you have in here, okay, its center is lying at 1 by 2, 1 by 2, 1 by 2 point. Okay, it's exactly at the center of the cube. Alright, so how we know that whether this plane passes through the center of this atom or not? How we can confirm that? Because there is a chance, like in some instances it happens that maybe the center is slightly here, away from where the plane is passing. So is that any way we can confirm that this atom is contributing to the plane, or whether this atom's center is lying on the plane or not? Is that any method? Yes, there is a method. Let me show you, because that was the point I was waiting for, to show you people that this is the method you can use to know that whether any of the atom on this planet is contributing to the plane or not. So that method is really easy, and let me show you that method, please. So we know that where the center of body center atom is lying. So the center of body center atom is exactly at the center of this cube, hence half for each of these coordinates. This is where the center of the body center atom is lying. And as I told you that if the center of the atom is lying on the plane, then that atom is actually contributing to the plane. If the center is not lying on the plane, then it means the atom is not contributing to the plane. Even if the plane is cutting the atom, but if it's not cutting through the center of the atom, then that atom will not be contributing to the plane. That is how we are taking it. Alright, so the center must lie on the plane. So if we want to see that whether this atom is contributing to the plane 1 1 0, okay, we want to check that whether this atom lie on this plane or not. For that purpose, we'll use equation of planes, which is x over a plus y over b plus z over c equals to 1. Okay, I'm gonna take this side, which is left hand side, which is x over a plus y over b plus z over c. Here e, b and c are the x, y and z intercepts, and x, y and z are the points that you want to inquire. Okay, so x-intercept, we know what is x-intercept. X-intercept was 1, y-intercept was 1, and z-intercept was infinity, the table that I established. So these are actually the values a, b, c, sorry, since I'm talking about intercepts. And what are x, y and z? X, y, z are actually these points that we want to inquire about whether these points lie on this plane or not. This equation actually tells you that which points x, y and z are lying on the plane. Okay, so you can inquire about any point and see that whether this point is a part of the plane or not. And we are inquiring whether this center is also a part of the plane or not, so whether the plane passes through this point or not. So let's put these values. X is half divided by a, which is 1. Y is half divided by b, which is 1. Z is half divided by infinity, which is c. So it's 1 over 2 plus 1 over 2, and we know that 1 over infinity or 1 over 2 in infinity, whenever infinity is in denominator, this quantity is 0. 1 over infinity is 0. So we got 1 over 2 plus 1 over 2, which is 2 over 2, 1. So we can see that is equals to 1, and this is left hand side, and it is equals to the right hand side. Right hand side was 1. So whenever left hand side is equals to right hand side, so that means that this point is lying on the plane. So 1 by 2, 1 by 2, 1 by 2 lies on the plane. On the plane, which plane that we considered was 1 1 0. So this point lies on the plane, and hence the center of body centered atom is intersected by the plane, and hence the body centered atom is contributing to the plane. Alright, so that's the good news that we have seen, that the body centered atom is contributing to the plane, and we can see that the whole of the atom is contributing to the plane. Okay, it's cutting it completely. So we will take this atom's contribution as 1, because whole of it is contributing to the plane. We can see it, but here the corner atoms, we can see that not all of it, but this part which is defined by these joining lines of the plane, okay, is actually inside the plane. This part is inside the plane. This part is actually inside the plane, and rest of all is outside the plane. Okay, and we need to calculate for each of these atoms that what fraction of them is inside the plane, and the similar method will help in here, which is we'll divide the angle between these two consecutive lines, okay, which is theta, let's say, and we'll divide it by the total angle of the circle, which is 360. We can know the angle, which is 90 degree, as I told you people that how it's 90 degree. So we'll divide 90 degree by 360. So it's 1 over 4. We'll get the same result for this atom, and for this atom as well, because the angle is same for them as well. 90 by 360 will give 1 over 4. Here 1 over 4, here 1 over 4 as well, and here 1 over 4 as well. Hence, the atom's contribution to the plane could be easily calculated by finding out the inner angles
that the plane has. Okay, all the inner angles needs to be calculated, and we will find out the ratio of each of these inner angle with a 360-degree angle. Why 360-degree angle? Because the cross section area of this atom is circular and the total angle of the atom is 360. So we are dividing that what angle or what part of it is inside the plane, which is actually the inner angle of the plane, and divide it by 360 degree, and we are boom getting the contribution of that atom to the plane.
So we can see 1/4, 1/4, 1/4, 1/4 and 1. Let's add them together and they will give us the net number of atoms lying on the plane. So capital N equals 1 plus 4 times 1/4, since they were all same, so we can simply write it like that. 4 and 4 cancel, so we have 1 plus 1, which is equals to 2. So 2, net number of 2 atoms lie on this plane. And we have this as the area of the plane, so let's divide them together to get the planar density. Okay, so planar density equals n over a. We can write in subscript like the Miller indices of the plane. Yes, here as well, 110. So we can put the values in here, which was 2 divided by under root 2 a square. Alright, so here we can also write it like that. 2 over under root 2 is under root 2 over a square. Okay, in shortcut, whenever this situation happens, like if it's 3 over under root 3, so the greater power holder, like it's 3 to the power 1 and it's 3 to the power 1 by 2. So wherever the greater power is, you'll write it like that. Okay, if it would have been under root 3 by 3, so you'll write it like that. And there is a way to prove it, like it's 3, here it's 2 to the power 1 and here 2 to the power 1 over 2 a square. We can take it upward, so it's 2 to the power 1, 2 to the power minus 1 by 2 now. Since bases are same, both of the powers have similar base, which is 2, so powers will be added. If you add up the power, it is equals to 1 over 2, so it's actually 2 to the power 1 over 2, which is under root 2 over a square. That is how you can prove that. And this is the planar density for 110 plane in terms of lattice parameter. And in BCC structure, we had a equals 4r by under root 3. This is the relationship between lattice parameter and atomic radius in BCC structure. So we can put it right here. So the square of them is actually 16r squared by 3, and 1 over a square is actually 3 over 16r squared, reciprocal of it. So let's write it here, putting into into 1 over a square, which is 3 16r square, and 3 under root 2 by 16. We can write it as 2 multiplied by 8 r square, right? So it's 3 by 8 under root 2 r square. Okay, so you can write it like that, or even this would be fine as well, whatever is comfortable for you. So 3 by 8 under root 2 capital R square, capital R square. This is the atomic density. This is the planar density in terms of atomic radius. All right, and it's for 110 plane in BCC. And what about the units? What are the units for planar density? Units are actually atoms per meter square. Okay, since it's plane, it's area, so we have per meter square, and you can even write it like that, atoms space per meter square. Okay, this slash means it's in denominator, and you can write it like that if you don't want to write the denominator stuff. So for example, you got 2 multiplied 10 to the power 22 result, so you will be writing atoms per meter square as its unit to complete the answer. Okay, so that is the unit, and we have done it for 110 plane. Now let's do it for the 111 plane.
Create the planar density for 111 plane in BCC. Now, this is the most controversial plane for BCC because there were so many people who were asking me that why the central atom in BCC doesn't contribute to the 111 plane and in planar density calculation. Okay, so this is a kind of thing that I didn't answer before and now I'm answering it, so stay tuned. Quickly get started with this planar density calculation for 111 plane. And the first thing that we do in calculating the planar density is to draw the plane. Okay, let's start drawing it. So we have the first square box, then another square box, and I hope you people know how to draw planes when we are given with Miller indices. And 111 plane is such a common plane, we just remember how to draw it. So it has one as x-intercept, one as y-intercept, and one as z-intercept. So this is one on z, and this is one on y. So linking them together through a straight line gives us the plane. Okay, this is the plane, and we can even shade it if we want, but we don't need it exactly because we know we want to calculate some other things. And that is the plane 111 plane, and you can see here that it's in triangular form, and to be specific, it's an equilateral triangle. By equilateral triangle we mean that all the sides of this plane are equal in length. Okay, this is equals to this length and this length, and we can even confirm it. We know that this lattice parameter is a, and this lattice parameter along y is a, and this length is also a. Okay, using the Pythagoras theorem we can find out the length of this hypotenuse. This hypotenuse has the same length, and we can see that this is the triangle here. Okay, it has base a, it has perpendicular a, and hypotenuse is, let's say this length is c, and same cases here. This is the base a, this is the perpendicular a, hence it will also have the similar c side because they have both sides equal. Okay, they have similar sides, so we can calculate this length, as that length will be used to calculate the area. So c is equals to c squared is equals to a square, which is base square, plus a square, which is the perpendicular square. And we can yeah, that is from Pythagoras theorem. We can write that this hypotenuse square equals to base square plus perpendicular square. So c square equals to 2a square, and c is actually equals to, taking under root on both sides, so it's under root 2a. Alright, so this is the hypotenuse, and this length, the same length will be calculated and obtained if we do the calculation for this side and for this side as well. So all these lengths are equal to each other. Alright, now let's see what is the formula that we use to calculate the area of the plane. Area of triangular plane equals 1/2 height into base. Alright, and we can see that this is the base of the triangle. Okay, this is the base of the triangle that we already know and we have already calculated, but we need to know the height of the triangle, and we can do so by finding out the length that we have for this point to this center point. Okay, we need to calculate this length, like this vertical length, and this is actually the height of this triangle. So let's do that calculation, and it would be better to denote them by some symbol so that we can refer to them. It's, let's say it's capital A, and let's say this point, this centermost point, is capital B, and we need to know their coordinates because we'll be using the distance formula to calculate the length right away, which is really easy method. And we know the coordinate of this point. Okay, coordinates means how much we have to move along x, y, and z to reach to that point whose coordinates we wanna calculate. So starting from origin, this is origin, I'll move 1 unit
along z-axis, 1 unit means to the other corner of the unit cell, and I have reached this point, and I do not need to move along x and y to reach that point. So it's 0 along x, 0 along y, and 1 along z. So that's the coordinates, and this point is at the center of this xy plane. So what I have to do is to move half unit along x and half unit along y, and I have reached this point. So 0 units along z. The coordinates of point B are actually 1/2 along x, 1/2 along y, and 0 along z. So these are the coordinates. Well, okay, now next we need to calculate this AB length, which is actually the height of this triangle. The AB length is actually the height of this triangle, and it is equals to x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square, and it will be multiplied by the lattice parameter because we have the lengths in a unit, so we need to multiply with lattice parameter. And here x2, y2, and z2 are the b coordinates, and x1, y1, and z1 are the a coordinates. Let me write the a coordinates here, which are 0, 0, and 1, and b coordinates are actually 1/2, 1/2, and 0. Let's put value right here to get the height. 1/2 minus 0 whole square, 1/2 minus 0 whole square, 0 minus 1 whole square multiplied by a. Next, 1/2 whole square, 1/2 whole square plus minus 1 whole square into a. It's actually 1/4 plus 1/4 plus 1 into a, and it's 1/2 plus 1 into a, and it's actually under root 3/2 into a. You can find out the LCM, and this is the height. Now we can find out the area of the triangle. Area A equals 1/2 height, which is under root 3/2 into a, into base, which is under root 2 into a. This 2 in the under root and this 2 cancels out, and we have under root 3/2 a squared as the area of the plane. We have successfully calculated the area of the plane right away so easily, and now we need to calculate the net number of atoms lying on the plane. Okay, for net number of atoms lying on the plane, we can see here that obviously we have these corner atoms, and these corner atoms are contributing to the plane. How? Because we can see that the center of corner atoms lie at the corner of the unit cell. We can see here that this is the atom in here, and the atom center is here, and we can see that the plane is cutting through the center of the atom. Whenever you are calculating the planar density, only those atoms are contributing to the plane whose center also lie on the plane. Okay, if atom center is not lying on the plane, then that atom will not be contributed as part of the plane, no matter whether the plane is intersecting the atom or not. Okay, that doesn't matter. The atom's contribution to the plane will be considered only in a case when the plane is also cutting through its center. If it's not cutting through the center, if it's cutting through any other point, then that's not acceptable, and that atom will not be contributing to the plane. So we can see here that its center is here, and the plane is also passing through this point, so that atom's contribution to the plane will be considered. Similarly, this corner atom will be considered because atom center is at the corner point and the plane is passing through this point. And similarly, we have this atom. We'll see how much of them are contributing. Like we can see, not all the atom, only this much of atom is inside the plane and not all of it. So we'll calculate the contribution of each of these atoms. And other than that, what about the central atom? Let's start the inquiry, and we are doing that inquiry for the centered atom, that is the body centered atom. And we know that where is the center of this body centered atom is located inside a cube. This body centered atom is actually right at the middle of the cube, so its coordinates are simply 1 by 2, 1 by 2 and 1 by 2. These are the coordinates of the center of this body centered atom, okay, because it's located right at the center of the cube, so that's obvious that these are the coordinates of its center. Now we need to check that whether the center point, like whether this center point is lying on this plane or not. That is the inquiry. All right, so let's do that, and we'll use this equation. Let's call it as x is equals to 1 over 2, y equals 1 over 2 and z equals 1 over 2. These are the points of the center of the body center atom for which we want to have the inquiry, and we have these intercepts, and the plane was 1 1 1. So the intercepts were these. We should write them first hand, then we can put them right away into the equation of plane. So putting into equation of planes, so what we get is x over a plus y over b plus z over c, that is equals to 1. This is the equation of plane, and I'm going to take the left hand side only, and we have this left hand side. Let's put the value in here. X is 1 over 2 divided by a is 1, y is 1 over 2 divided by b, which is 1, z is 1 over 2 divided by c, which is 1. So it's simply 1 over 2 plus 1 over 2 plus 1 over 2, and that is equals to 3 over 2. And we can see that this is the left hand side and it is not equals to the right hand side. Right hand side is 1, and we can see they are not equal to each other. Hence the left hand side is not equals to the right hand side. This means that this point is not lying on the plane, which means the center of the body centered atom is not lying on the plane, or the body centered atom is not centered on the plane, and in that way we have seen that the body centered atom is not contributing to this plane. Alright, so we'll not be considering this body centered atom as contributing to the plane, and only these three atoms are contributing to the plane. Alright, so they will be considered, and let me show you that how we can prove that these atoms are also contributing to the plane, other than the fact that we can see that obviously their centers are at the corner of the unit cell, and the plane is also intersecting the corner of the unit cell, so obviously they are contributing to the plane. But just for the sake of elaborating this method, I wanna show you, and I'll also do that inquiry for this, let's say this atom, and I'll show you that how this method is magically working for us, and you can use it for any kind of unit cell, okay, whether it's FCC, BCC, hexagonal or whatever. Okay, you just need to know how to use that method. So let's find out this atom's coordinates and check whether this center lies on this plane or not. Okay, so the coordinates of this point are really simple. Starting from origin, you just have to move 1 unit to reach that center point. So its coordinates are 1, 0 and 0. Since no motion along y and z were needed, so these are its coordinate. Let's put this equation, this point, this is x point, y point and z point, into this equation. Okay, a, b, c are same because the plane is same. So let's put in here and see what we get. It's x over a plus y over b plus z over c. Put the values. It's 1 for x divided by 1, y is 0 divided by 1, z is 0 divided by 1. So it's 1 plus 0 plus 0, that is equals to 1, and it is actually equals to the right hand side, which is 1. Okay, you can see the right hand side is always 1, so you have to check that whether the left hand side comes out to be 1 or not. So that is the basic thing that you need to test. We can see that it is equals to 1, hence this atom whose center is located at this point is contributing to the plane. That is how you decide. Now let's decide for this atom, okay, as well, just for the sake of understanding the method. So its center is located at this point, and starting from origin, you'll move 1 unit along x and 1 unit along y. This is y direction, so 1 unit along y to reach that point. So 1 unit along x, 1 unit along y and 0 unit along z. So you reach that center point, which is the center of this atom. So let's see whether this is intersected by this plane or not. So we can run the inquiry. X over a plus y over b plus z over c, and plane is same, 1 1 1, so 1 over 1 1 over 1 plus 0 over 1. So it's 1 plus 1 plus 0, that is equals to 2. And that is not equals to the right hand side, which is actually 1. So we can see a systematic way in which we can see that which atoms are contributing to the plane. If center is part of the plane, all right, then it's contributing to the plane. If center is not a part of the plane, then it's not contributing to the plane. And that is the equation of plane that will tell you. Use the left hand side and see whether it is equals to the 1 or not. If it's equals to 1, then that atom is contributing. If it's not equals to 1, it's not contributing to the plane. And that's the really simple method, and you can use it every time. You just need to find out the coordinates for the center of the atom for which you want to have this inquiry, and you can do it obviously for all of the atom or for the atoms for which you are confused, and this will give you the the exact answer, yes or no answer. There is no confusion left. And keep that in mind. This method only tells you that these atoms are contributing to the plane. It doesn't tell you that how much. It doesn't tell you that how much of the atom is contributing to the plane. As you can see that not all of the atom is inside the plane. Only that much of the atom is inside the plane, which is decided by this boundary line of the plane, or the angle between the boundary lines of the plane, the inner angles. Okay, these inner angles of the plane decides how much atom is contributing to the plane, and we call this as theta. Okay, and since the atoms are circular, so the total angle of circular atom is 360, and you can find out each atom's contribution to the plane by dividing the theta angle by 360, and you will see that is how I'm gonna do it later on. I'll use the previous figure as well, so we'll use this thing every time where whatever the plane is, whatever the cubic structure is, whatever the unit cell is, whether it's FCC, BCC, hexagonal or whatever. Okay, this method always works. So let's get back to the video where we were. Now let me proceed with what we have in here. So we can see there that these are the three atoms that are potentially contributing to the plane, and not all of them is contributing to the plane. So how we are supposed to calculate their contribution? So here what we will do is to find out this angle, which is actually theta. Okay, we'll calculate it right away, and we'll compare it to the total angle of the circle, which is 360. We'll find out the ratio. The ratio is actually the contribution of atom to the plane. Okay. It's an equilateral triangle. The total angle of a triangle is 180. Okay, the sum of all the angles is 180, and for an equilateral triangle, equal angle is distributed among each of them, so it's 60 degree, hence theta equals 60 degree in here. Only in equilateral triangle all of the angles are 60 degree. All right, so this is 60 degree, and the total angle of the circle is 360. So the atom's contribution to the plane is 60 divided by 360, which is 1 over 6. Okay, so 1 over 6 by this atom, 1 over 6 by this atom, 1 over 6 by this atom. So what is the total contribution? Capital N is equals to 3 times 1 over 6, because there are 3 of atoms, all of them have same, so 3 ones are and 3 twos are, so it's 1 over 2. That is 1 over 2, and let's find out the ratio, and let's put the value right here, and 1 1 1. In BCC it's 1 over 2 as total number of atom divided by under root 3 by 2, and multiply by a square. So this 2 goes up, 2 and 2 cancels out, and it's 1 over under root 3 a square as the planar density for 111 plane in BCC. Alright, so this is the formula in terms of lattice parameter, and we can convert it into atomic radius, and for that purpose we know that the diagonal length is 4r. Since all the diagonal atoms are connected to each other, so this is 1r, this is 2r, and this is another r, so r, 2r, r is 4r. Okay, and this length, what does this length is in terms of a, if you know directly the relationship between atomic radius and the lattice parameter in BCC, you can directly use it, but you can even derive it if you forget it, so you can derive it. So this is the diagonal length, this is length a, and this length is under root 2a. We can easily calculate this length in terms of lattice parameter as well. This is a square plus this is under root 2 a whole square, that is equals to this length, which is actually c square. I'm gonna call it c square or d square. A square plus 2a square equals d square. This is 3a square equals d square, and d is actually under root 3a, and under root 3a equals 4r, and hence a is equals to 4 by under root 3 capital R. So we can put the value right here to get a equals 4 by under root 3r, squaring both sides to get the value of a square. It's 16 by 3 r square. We can put the value right here to get the value of expression of planar density in terms of atomic radius. So it's under root 3. 3 by under root 3 is actually under root 3. You can do this on calculator. And under root 3 by 16 r square. This is the planar density in terms of atomic radius. And this is the atomic density, planar density in terms of lattice parameter, and they have units of atoms per meter square. Okay, whatever results you are going to get, for example, you get 2 multiplied 10 to the power 20, so you are supposed to write atoms per meter square as its unit of planar density. Okay, so or you can write it like that as well, atoms space per meter square. Atoms shows that we have number of atoms right here on the numerator, so this is the planar density of number of atoms. Okay, how much atoms there are on the plane, so that is why we are writing atoms. We can even write it like that as well, but that's more perfect. Okay, that is it for this video. I hope you are clear now. All right, so here I have mentioned all of the steps that you are supposed to follow.
Well, that is it for this video. Keep watching and goodbye.